So let's talk about handling missing values in state space models. I already mentioned that is one of the attractive properties of state space model approach, right? That it can handle missing values easily. So if you look at standard statistical packages which estimate ARIMA models, you often notice that some of them do not handle missing errors very well. Now in Python, the SARIMAX handles missing values very easily. Why? Because SARIMAX underneath, as I mentioned, uses state space modeling approach, and in state space modeling, handling missing values is easy. So how is it done? So I'm going to show you an example of doing it with my example in this data set. Now, it actually can get quite, not convoluted, but it's quite involved, I would say, for more complicated vector models and so on. But for this very simple model, it turns out that it's going to be very easy. You can find it in the section 6.4 of the Shamwo and Stoffer's textbook. But basically it boils down to modifying those filtering equations in Kalman filter. We remember there were 5 filtering equations. So there was something called Kalman gain, and we are setting it to 0. So the Kalman gain had some some formulas. It was very simple, but there was something going on. Now we're just saying there's no gain, 0. We're saying prediction error is 0 because we are not observing the data is missing for this period. So in this particular period, there's no YT. We cannot calculate prediction error, so we'll set it at 0. Now, surprisingly somewhat, the variance of prediction error is going to be set to 1. Why 1? So one part is a little bit weird, right? We'll talk about it in a second. Now, the hidden state is not changing because we're not getting any more data, so we'll just we'll get the previous hidden state estimate and just progress it to today. Now, today's hidden state estimate is going to be my yesterday's. I didn't observe any data, I'll just continue it. And the variance is the same, going to be my old previous forecast of the variance. So let's look at this sigma. Why is it 1? We can actually see it very easily here. Remember the maximum likelihood function. Sorry, likelihood function, log likelihood function. Let's see. Here, you see, we are using here sigma here and sigma there. So if we plug now this missing value, so for the missing period t, only for the missing period t, we're plugging the error as 0, right? We said we'll put 0. So this second term is going to be 0. Good, so it's gone. But for variance for this particular period with missing data, we're inserting 1. Why? Logarithm of 1 is 0. So that's how if we put sigma 1 and error 0, then the contribution of this period t with missing data to log likelihood is going to be 0. It's not going to contribute anything. That's why. So now let's go to missing values. Right, so if we do that, then we can just apply our old Kalman filter, right, with just modified equations. And that is what I'm doing here in this cell. So if we look at this cell, it is basically the same Kalman filter, but I called it filter M. The only thing that is changing here, I put this checking for null. So if my Y is none, sorry, not null, but not a number. So if the Y is not present, then I'm saying my epsilon is 0, sigma is 1, K Kalman gain is 0, and I'm leaving my negative likelihood intact. Why? Because the contribution from this data period will be nothing. And to run my test, I'm doing the following. I'm creating the copy of my data, right? My inflation, PCE inflation data from Fred. But then for about 2 years, in 2016, 2017, 2 years worth of data, 8 periods, I'm setting them to not a number, and that signals to my code that the data is missing. And what am I getting? If I run this filter, I am going to, well, I will minimize, actually I have a log likelihood, so I can minimize my code, minimize my log likelihood, and I'm getting this kind of a chart. So let me explain. So the blue line again is an filtered value of x. as we've done before. However, now I took 2 years of data in 2016 and 2017, and then I basically removed that data. I made it missing. And when I did that, this is missing data. We are not observing these red dots. It's missing data, but I am able still to calculate or to estimate my state. So the missing data was not an issue to estimate my state. So this is a very simple way of handling missing data for this case. But again, it can get quite complicated if you have a vector regression. All right, so we'll talk about sampling frequency in a second. But basically, if you have a data set with multiple observations, you're observing multiple economic variables, and some of them are missing in some periods of time, then you can use this missing data approach. It will be more complicated, of course, because the one I showed you here is only for a very simple model that we're using in my example, right? Now, this missing data approach actually can be used for mixed sampling frequency. So think about two situations. Think of this. You have a data set where you collected the data with, let's say, GDP and unemployment. Unemployment is published by Bureau of Labor Statistics, BLS, monthly, while GDP is published by BEA, Bureau of Economic Analysis, quarterly. So one of them comes at quarterly frequency and the other one comes at monthly. So what you can do with this missing data approach is basically have the monthly frequency of the data, but when it comes to GDP, you can put GDP as empty, as NaN, as missing for those 2 months each quarter. You're not observing GDP. So that's one approach, right? So that way, the higher frequency data will be your frequency of entire data set, and lower frequency data will have missing data. But then applying a similar approach, you will be able to easily overcome this problem. So you can have data at different frequencies of sampling. Another thing can happen is sometimes when you're collecting the data, older data comes at lower frequency. So imagine you have a data set where initially they were collecting the data annually, and then they switched to quarterly, and then they switched to monthly, and now you have this monthly data set, but you want to use your old data too. So what you can do, you can set a monthly frequency, and then when it was slower than monthly, you will just put empty, like missing data points. That's another approach, right, for your modeling, which you can use the advantage of state space modeling. Now we're done with this introduction, so I will summarize what we've learned in this lesson, and that's following. We looked at a very simple state space model example, and we've learned a few key concepts of this technique, which has its centerpiece a Kalman filter. So we learned a Kalman filter, and we've learned that Kalman filter has the concepts related to it called predicting and filtering. So Kalman filter does prediction and filtering. There's another facility called Kalman smoother, which does smoothing, right? So predicting means we're estimating our state using the data collected in the prior periods. Filtering means we are estimating the state for the period t, including the data in period t, while smoothing means we're using entire data sets. So we might be using data sort of from the future to estimate better our like think of it, the whole data set, and you are getting the better estimate of the state variable in the middle of the data set by using the entire data set data. So we've learned all these concepts. We've implemented them in Python code. We also implemented the maximum likelihood estimation, because Kalman filter can easily produce the log likelihood, which we can use then to iterate through different sets of parameters and find the best optimal set of parameters. And we applied this to fit the model, this very simple model, to PCE inflation, and we saw that its long-run estimated long-run mean inflation actually is consistent with Fed's targets of 2%. Hooray. And then we found out that, oh, wait a second, state space model framework is very flexible and can be used to represent a very big variety of different models. So we didn't look at all these different models, but we looked in particular at ARMA 1.1, and we've learned that our model actually is ARMA 1.1. And then, like I mentioned it, we didn't go in details, but basically I said there is very, very big variety of different models that can be represented as state space models, and the reason for doing so would be is this efficiency of Kalman filter. It's very fast filter, right? Because we said it uses this recursive procedure to quickly calculate filtering and smoothing, and it also has this capability to handle missing data relatively easy compared to some other approaches. Now, having learned all of this, I hope that now you're in a good position to actually start learning more about state space models. Hopefully you will be able to more efficiently use the packages such as SariMax. They're using filtering, they're using smoothing terminology. You'll understand better what they mean when they say filter smooth, and you will be it will be easier for you hopefully to read the textbooks on state space models or advanced time series, right? Now there's a lot to learn because it was a very limited exposition, very limited example here. So for instance, I only looked at univariate series, but the power and flexibility of Kalman filter is coming from its handling of vectors. So states can be a vector, and observed variables y are also vectors. And then you have all these matrices and so on. So it can be very flexible because of the vector nature of the equations. But we didn't look at that. We only looked at univariate series. Now we assumed only linear models. My model was linear, Kalman filter was linear, and so on. It doesn't have to be linear. There are non-linear Kalman filters. They get kind of complicated, and they're not as, I guess, robust as linear ones, but they are there for you to use if you're interested. Now, the big limitation of our example was constant parameters. So that like constant in our state equation was constant. The coefficients, a lot of coefficients, everything was pretty much constant. But Kalman filter allows for time varying coefficients. Now again, they are not as robust as constant, but they are there for you. Now we assume that the errors, observation errors and the state innovations are uncorrelated. But in state space model, that doesn't need to be that way. You can actually have correlated measurement and state errors, right? So basically these limitations can be relaxed or lifted, and the state modeling approach is quite, is very flexible, and it allows for a lot of different configurations and setup, but then it gets very complicated. So hopefully you are in a better position to start learning about all of that. Thank you.